Hi. Okay, so now we're going to dive into the chemical potential, and I want to talk about the effect of temperature on the chemical potential. So in this section, chapter 4, we are assuming that we have 1 molar system. So the Gibbs energy in terms of moles, or molar Gibbs energy, is equal to the chemical potential, which is a function of both P and T. So the chemical potential is actually dG dN, where the number of moles changes is equal to the chemical potential. But if this is only going to be for a 1-component system where you only have 1 type of mole, G molar becomes mu molar. Okay, so that's a very important indicator, very important point, because next chapter, when we're getting into mixtures, this is where we introduce chemical reactions into our thermodynamic potentials that we've been using. That's to come. Right now, molar Gibbs is equal to chemical potential. So the same way that we derive the different changes in the Gibbs, we can do the same thing with d mu is equal to, and so now we're going to look at the total differential, because this is both a function of pressure and temperature. How does mu change when I change pressure, multiplied by the actual change in pressure, plus how does the chemical potential change when I change temperature, multiplied by the actual change in temperature. And here we've got T held constant, and here we've got P held constant. From the Maxwell's relations, we know that the change in the Gibbs with respect to temperature at constant P is equal to minus entropy. So this is the molar Gibbs, which means this will be the molar entropy. And change in Gibbs, change in pressure at constant T is equal to the molar volume. Or it would be equal to the volume, but because we've got the molar Gibbs, this is now the molar volume. Ta-da! Okay, so because of this, we can say that this is the same as saying d mu molar dt at constant T is equal to minus S, and likewise d mu molar dP at constant T is equal to molar volume. Groovy. Okay, so now you can hopefully see that this bit is, oops, I got them backwards. This bit is over here, and this bit is right here. So now I'm going to re-erase and rewrite. Pause. Okay, so now I've got d mu is equal to V m molar volume dP minus S molar dt. I want to look at just constant pressure processes. So we're going to be looking at the effect of temperature on the chemical potential. So I'm going to say at constant P, this bit goes to 0. So I'm left with d mu is equal to minus S sub m dt. Okay, and what we can do then is say that this is the same as d mu dt at constant P is equal to minus Sm. So that brings me now to this plot of the chemical potential as a function of temperature. And what you'd get is 3 separate lines, one that's about like that, one that looks like this, and one that looks like that. And so I'd like you to take a minute and look at this figure and think about what each of these 3 different lines might represent as temperature is getting bigger. Remember that we've been dealing with phases in this chapter, sorry, in this focus. So this represents solid. The purple one represents liquid, and then the green one represents gas phase. So now I'd like you to think about what the slopes of each of these lines represent. So here you've got the slope is equal to minus Sm, and notice how these values are all decreasing, which means that S sub m has to be positive or negative. Positive, hopefully you said that. So because this number will be positive, you're always left with this quantity will be negative. Because you don't want this value Sm to be negative, because if it is, that means negative makes the quantity a positive, which means these lines would all be going up, which means your chemical potential would be increasing as you increase temperature. Not cool. Think about why that is. Okay, so each of these represents the different slopes. So this is minus S of your solid molar This one is minus S of your liquid, again, molar, and this is minus S of your gas, again, molar. So each of these slopes represents the different entropies associated with the phase that you're in, solid, liquid, or gas. Question: why is it that the entropy for a gas is greater than the entropy for a solid? And this is absolute entropy, different than the change in entropy. Go team. Other thing to note on this plot, if we were to take this down, so this is T, what would this be? This would be going from the liquid phase to the solid phase, so this would be T of fusion. And then here you have T of boiling, or T of vaporization, I should say, vape. T vape. Vaping is nasty. You shouldn't do it. Okay, sorry, that was personal thought. Okay, so you've got this region here between this temperature and this temperature, that's where the liquid exists. So that temperature range of the liquid between the solid and the gas is really defined as where your chemical potentials are bounded by the chemical potential of the solid and the chemical potential of the gas. Cool? Okay, I think that's all I want to say about temperature. Now what we're going to do is we're going to do this exact same thing, but instead of investigating the temperature, now we're going to investigate what happens when we change the pressure. Go team. Go team. Now we are in, I'm realizing that it's go team back to back, whatever. So d mu is equal to Vm dp minus Sm dt. At constant t, this term goes to 0, and we're left with d mu dp at constant t is equal to V sub m. Go team. So you can plot mu versus pressure. I'll make this a pressure, and you can get your molar volume that way. Just like we did with the other plot, but instead of it being that the molar volume for a solid will be greater than for that for a liquid, you'd have something that looks more like this, where you've got your gas, your liquid, and then your solid. Again, because your molar volume is going to be decreasing as you go to from your gas to your liquid to your solid. But I don't really care much about this pressure variation. I want to go back to the temperature variation, but looking at it as a function of pressure. And you might be thinking, well, Allison, how does that work? Because in order to look at the pressure, we really have to keep temperature the same. That's true. Let me show you. Okay. Temperature. So I'm going to go back to the plot that we had before. So here's my solid, my liquid, and my gas. Okay. These might be drawn a little extreme, but I want to exaggerate the differences. Solid, liquid, gas. Okay, and this is at T1. Or sorry, this is at P1. Okay. Now, if I change the pressure to let's say a lower pressure, so so P2 is greater, or P1 is greater than P2. What happens now is that at a different pressure, I'm going to have this exact same trend, but it's going to be shifted a little bit. And so let's say it's going to be, I want to get this right. Yeah, so P2 is less than P1, so I've reduced the pressure. So my line will look something like this. So here is P1 solid, but at a lower pressure, I've just linearly moved it down. Okay, so this is the solid chemical potential at P2. Is everyone following me? Okay. Now I do the same thing here, and actually I'm going to make this a little easier by saying we've got the green line. So now we've got the green line. And so I moved it down about the same. So if this blue line moved down to the purple line, this green one moved to the dashed line. And then likewise, let's make this one red. Cool. Okay. Does everyone see that, hopefully? Okay. So why am I taking the time to do this? Well, some really nifty stuff happens. So here on the original, okay, let's reassess where we are. We have our system at pressure 1, where our solid, liquid, and gas overlap. So this would be, those would be the phase transitions that you would see at pressure 1. Okay, let's reduce the pressure then. So let's say, I don't know, go up on top of a mountain. Yay, here's me, and I'm walking that way. Now I'm up on top of the mountain. Woo! Lower pressure. Okay, P1, P2. Let's see what happens with the chemical potentials as I go up the mountain and the pressure gets reduced. All right, so the chemical potential has reduced linearly by everything, or not by everything, linearly by all of them. And so these lines have shifted, which means, check this out. The original temperature difference, where this is T fusion and this is T or vaporization. Okay, so there's that line. There's that difference. The range in which the liquid phase is liquid. Okay, but then when we get here, because of this shift, this line crosses now here, and whoops, this line should actually cross. Yeah, that's right. And this line crosses, there we go. Yeah, that is right. This line crosses now way lower than the original T vaporization. Okay. So you've got this narrowing of the phase, the narrowing of the temperature range in which the liquid is going to be liquid phase. Cool? All right. So now we've got T vaporization is reduced, and so T vape is lower at lower pressure. And wow, that says lower. Sorry, lower. And so think about that. Go up to the top of the mountain. How hard is it to boil water? You can boil it at a much lower temperature. This is an indication that you're going to have a reduction in the T vaporization for their process at a lower pressure because of the change in the chemical potential due to a lower pressure. Cool? Rewind and listen to that part again.